here's the good news. If you have a basis that is also an orthonormal basis, then you don't have to solve the system of equation in order to find these coefficients actually. So that every vector can be written very easily as linear combination of UIs, which are these bases. The question is, what are going to be the coefficients here? So if you want to write V as a linear combination of UIs, then you need some AIs, UIs, and those constants previously we were trying to find through system of equations, but now you can easily find those coefficient very easily without getting into too much detail by simply taking the inner product of the vector V with each of the vector ui. Okay? Then if you take vector V and compute its inner product with the ui, that will be the coefficient of the ui. Okay? So it's very easy. So you don't have to solve this system of equation in order to find such a coefficient. Just take V and take its inner product with ui. Simple. And if you want to compute, for example, the magnitude of V square, then this is not difficult, because this really follows from, then this would be equal to I equal to 1 to n. Take these coefficients and compute their magnitude and square it and sum them over 1 to n. Okay, so these are the two properties. So if I have a finite dimensional vector space, inner product space with an orthonormal basis, then any vector can easily be written as a linear combination of that orthonormal basis. The coefficients are going to be VUI, and its magnitude can be written as, simply take these coefficients, square them, and sum them up to 1 to n. So this is what that I would like to prove. So why this is the case actually, so maybe you can help me out in proving it. So let's calculate. So let's write let us write V as a linear combination of UIs actually. I equal to 1 to n, where these AIs are unknown, so we don't know that what these should be. My claim is that each one of these AI is basically this inner product, and let's see that why this is true. So let's take V and calculate its inner product with the UI. I know that V is this, so it's gonna be sum I equal to 1 to n AI UI. Maybe I must write a different index here, j. So you're gonna have AJ and UJ because we have already used I here. Okay, and you're gonna have UI, but I know that I can pull this sum out of inner product, so this would be j equal to 1 to n and AJ UJ UI. Okay, and but I know that this AJ, I can pull this scalar out of inner product, so I can write my AJ here. But then UJ and UI are what? So since UIs form an orthonormal system, so this will be equal to I equal to 1 to n, AJ and delta IJ. Okay, AJ and delta IJ. Now what would be this product actually? So I know that this sum is going to be A1 delta I1, A2 delta I2, and then one term will appear AI delta II, and then final term is going to be in this sum AN delta IN. Okay, delta IN. So So we know that all of these delta ij's are 0 when I is different from j actually, or j is different from I. And it's going to be equal to 1 when I is equal to j. So this would be equal to, after expanding and using this definition, this would be equal to ai. And hence we showed that our unknown ai's are now known to me. In order to find the coefficients, you just need to do what? Take your vector v and just take its inner product with what do you call ui, and you're going to get such a coefficient. Okay? And hence we proved this. The first one is done actually. This is really a direct consequence of what do you call our generalized Pythagorean theorem that we proved, because if you take v square, which is v is the sum of I equal to 1 to n, so we know that if the v is ai ui square, that we just proved that previously that this would be equal to I equal to 1 to n ai square, but we proved that ai are vui, so this would be equal to I equal to 1 to n v ui, and its magnitude is square actually, so this completes the proof. Okay, so what does this theorem is telling you? This beautiful theorem is telling you that if you have a finite dimensional inner product space and you have a basis of orthonormal and you have an orthonormal basis, then what you can do is that then any vector can be represented very easily in the terms of these bases as this combination actually, as this combination, okay? Where these coefficients, you don't have to solve the system of equation for finding the coefficients, okay, of the ui. Just take the inner product of v with the ui, so that would be the coefficient of ui. And its magnitude is simply take these coefficients and square them and sum them, that would give you the magnitude actually. Okay? So for a finite dimensional inner product space, orthonormal basis rocks. Now here is the next interesting question actually. Okay? The next interesting question. The next interesting question is, I mean, we know that not every basis is an orthonormal basis. Okay? So not every basis is an orthonormal basis actually. So what to do? So imagine I have been given an inner product space. So I have an inner product space where I have a, some geometry problem that I would like to solve. And I know that my geometry problem is going to be difficult, if you are solving it with the kind of bases that are not orthonormal, then what to do? So what we can do is that you can take any basis of what do you call an finite dimensional inner product space, and you can turn that basis into an orthonormal basis. Okay? So an orthonormal basis. So if you want to, for example, solve your geometry problem, okay, in an inner product space where you don't have orthonormal basis, so first do what? Turn your non-orthonormal basis into the orthonormal basis, and then solve your geometry problem actually, or then do your calculation. So you will see that you can do things much easier way. So if you don't have an orthonormal basis for finite dimensional vector spaces, don't worry, you can always turn your non-orthonormal basis or any basis into an orthonormal basis, and you already know the recipe, because in your first linear algebra course you have done what you call the Gram-Schmidt process. Because Gram-Schmidt process is doing what? You take, for example, 10 vectors or n vectors, then you can turn those 10 vectors or n vectors into orthonormal vectors using the Gram-Schmidt process actually. So in other words, using those 10 vectors, generic vectors, you can construct the 10 orthonormal, what do you call, vector. Okay, so imagine I have an inner product space for which a finite dimensional inner product space for which I know there is some basis, and I want to turn that basis into what do you call an orthonormal basis. Then how can I turn my generic basis, the general basis, the basis that is not necessarily orthonormal, into an orthonormal basis? The answer is simply apply the Gram-Schmidt process. Because if you can apply the Gram-Schmidt process, you can turn your non-orthonormal basis or general basis into the orthonormal basis actually. Okay? So, since you already know what is how to deal with the Gram-Schmidt process, so I'm not going to spend too much time on it. I'm not going to spend too much time on it. I'll just write that algorithm and write some consequences of it actually. Write some consequences of it. So, how to turn, so the question that we would like to answer, how to turn a given set of vectors, say v1, v2, vn, okay, in a finite dimensional vector space or any vector space or in a product space, in a product space V into an orthonormal system u1, u2, u3, un actually. So in other words, using these vectors, can we create n orthonormal vectors? The answer is yes actually. So the answer to this question is certainly yes. Okay? And how can we do it? Through Gram-Schmidt process. Okay? Through the Gram-Schmidt process. Okay? So I don't know about in your previous course of linear algebra whether you have done a proof actually that why Gram-Schmidt process works actually. Okay, why this algorithm works, why this algorithm can always take non-orthonormal vectors and can turn them into the normal vectors actually. I mean, if you haven't seen that proof, please let me know in the Zoom sessions so that, you know, in my next discussion or in my next recording of the video lecture, I can discuss that proof as well actually. Okay? Or if you think you need some explanation on Gram-Schmidt process, I can record a lecture on Gram-Schmidt process in its detail and its proof and so on and so forth. But at the moment, I'm assuming that you know the Gram-Schmidt process directly, so I'm going to just recall and review the Gram-Schmidt process actually. Okay? So how to do it? The answer is, imagine you have been given a set of n inner product, n vectors in a product space, and you want to construct what do you call the n orthonormal vectors actually, or you want to construct a system of n orthonormal vectors. Okay? So here's the thing. So your first orthonormal vector u1, we know, is going to be what? Take your first vector v1 and simply normalize it. Divide it by the magnitude of v1. Okay? Divide it by the magnitude of v1 actually. So that would be an orthonormal vector. So the u1 then is going to be an orthonormal vector. What would be u2? Okay? So if you remember that u2 is going to be that take your v2 vector, okay, take your v2 vector and do what? And subtract what? Subtract the inner product of v2 with u1, okay, v2 with u1, and divide everything by the norm of the same vector actually, okay, the same vector. Shall I write in a bit more different way? So for example, if I say that calculate first, say, a vector xk by x2, and then x2 is what? x2 is v2 minus the product, inner product of v2 with u1. Then your u2 vector is going to be the x2 vector divided by the magnitude of x2. In other words, your u2 vector is going to be v2 minus v2 inner product with u1 divided by the magnitude of this vector, which is v2 minus v2 u1 actually. Okay? So there is a whole explanation actually that why this algorithm the way it is actually. So as I said again, that if you think you don't understand this, that why the algorithm the way it is, please let me know in Zoom session so that I can have discussion with you and you can know it actually. So I can prove that as a theorem. I mean, it has to do with the orthogonal projections actually. So since I'm assuming that you already know this, so I'm not going to get into the details of it. So what would be then u3 for example? Okay, so take your v3 and subtract it and take the inner product of v3. I must say that here it should be u1 because this is in a scalar actually. So it should be u1 here and it should be u1 here actually. Okay. Now what would be u3? u3 is going to be take your v3, take its inner product with u1, take your inner v3, take its inner product with u2, take your v3 and take its inner product with what? With u2. With u2, so that will be the coefficient of u2, and divide everything by the magnitude of the same vector that you have above actually. Okay, the magnitude of the same vector that you have above. So if I write in generically that if I have to compute say ukth vector, where k could be anything 1, 2, 3, 4, 5 up to n, then what you need to do, you need to take your vkth vector and subtract vk in a product with u1 and multiply u1. I'll make this number the coefficient of u1 minus vk in a product with the u2 and so on and so forth. You have to subtract this all the way vk in a product with uk minus 1 coefficient uq. Okay, so this is what it is going to be, and then divide everything by the norm of the vector same as above actually. So this is what is really the Gram-Schmidt process. So in this manner you're going to get new vectors u1, u2, u3 and un, and you can turn your any vector, okay, any set of vectors which may be orthonormal or non-orthonormal into an orthonormal set of vectors actually. Okay? Into an orthonormal set of vectors. So what is the consequence of it? The consequence of it is that imagine you have a vector space or inner product space for which you have any basis. So what you can do, you can take that basis and you can turn it into an orthonormal basis actually. And as I said, once you have an orthonormal basis, for example, we will do the discussions on Fourier series, okay, you will see that it just kind of makes your life, makes your calculations very easy when your basis is an orthonormal basis actually. Okay, so this is what is going to be the case. So let me write this stuff in the form of a theorem, and then maybe I can quickly run through the theorem. So you have to keep in mind every single theorem answers an interesting question. Okay? So this theorem answers the question that if you have a basis for an inner product space which is not necessarily orthonormal, you can turn it into an orthonormal basis actually. Okay? So here's a lemma. But I have already said this lemma actually, so I don't need to rewrite this again. By the way, an interesting observation is, if you have these vectors, say v1, v2, vn, which are already orthonormal, then obviously it is silly to apply the Gram-Schmidt process onto it to turn them into orthonormal because they are already orthonormal. But what if you really apply the Gram-Schmidt process on these vectors out of curiosity to see that do you get new vectors as an orthonormal, what do you call, vectors? The answer is that if you already have an orthonormal system, okay, that is, and on that orthonormal system, if you apply what you call Gram-Schmidt process, then obviously you're going to get vectors u1, u2, u3, but you will see actually that these vectors are basically same as the previous vectors. So you will not get a new orthonormal vectors by applying the Gram-Schmidt process on it. So there is no need to apply Gram-Schmidt process on the orthonormal vectors, which are already orthonormal vectors, because you're not going to get anything actually. You're not going to get anything. Because, and the reason for this is this actually, because all these inner products are going to turn out to be zero actually. All these are going to turn out to be zero. And since all these vectors are going to turn out to be zero, you're going to get what do you call uk vector, which is vk by norm of vk, which is already orthonormal. Okay. So this is lemma 5.3.10 in the book. I would highly recommend to read that lemma and try to make sense of it for yourself. Okay. Because I have already kind of proved and discussed this lemma in detail. I would like to talk more about an interesting consequences actually. Here the corollary of all this discussion that we have. Okay. So here the corollary of the discussion that we have that every finite dimensional inner product space has an orthonormal basis. Every finite dimensional vector space in a product space, okay, as an orthonormal basis. And the proof is obvious actually. Think about it. Proof is obvious. So imagine you have an inner product space whose basis is this actually. So V1, V2 and Vn, for example. It's an n-dimensional vector space whose basis is this. And then I know that using the Gram-Schmidt, okay, using the Gram-Schmidt, I can turn these vectors into an orthonormal system. Okay? Orthonormal system. Now this orthonormal system is also going to be a basis for inner product space, and hence this basis is what you call the orthonormal basis. So something that I already said. So if you want to make your life easy, if you want to do the calculations, for whatever reasons that you want to do in the inner product space, through any basis, turn your basis using Gram-Schmidt process into orthonormal basis and see the magic. You will see that your calculations are going to be much more easy. Here is another question. Okay, here is another question. What if my, what if my vector space is, say, 10-dimensional? Okay? 10-dimensional. So we know that it's going to have, a basis that comprises of 10 vectors actually. Vector space, or maybe inner product space, is 10-dimensional. Okay? And I know that for this inner product space I have some basis, or maybe you don't know the basis of it actually. Okay? So the one way could be, so imagine you have a 10-dimensional Banach space, not Banach space, but inner product space, and for example, only two vectors, say u1 and u2, which are orthonormal to each other, which are orthonormal. Okay? So my space is 10-dimensional and I know only two vectors that are orthonormal. The question is, can I, using these two vectors, create an orthonormal basis for inner product space? In other words, can I take these two vectors, okay, and then create 8 more orthonormal vectors which form an orthonormal system and becomes a basis for inner product space actually. Okay? So this would be something interesting, because this is going to help you in the case. Imagine you know that the dimension of inner product space, but you don't know the basis actually, and you want to create a basis for it. Okay? So you have a 10-dimensional vector space and you don't know the basis of